Let's take a look at another induction proof. Now we're going to go back to the equality statements. And so this is the statement we like to prove. Prove that the sum of these odd numbers, the sum of the squares of the odd numbers is equal to this. So remember, we looked at the sum of odd numbers and we saw there's a really nice pattern. If you square these, then you also get a pattern. Not a very nice pattern, but it's a pattern at least. So this is going to be true for all n in the natural numbers, including 0. Okay, so if we think about our proof that we're going to do, if we do our proof by induction, we have our base case. What is the smallest value of n that this is going to be true for? Well, n equals 0. So we can say let n equals 0. Over here on the left-hand side, we plug in n equals 0, and all we get is the single term of 0 plus 1, which is 1 squared. So we see 1 squared is equal to 1. And then this right-hand side, if I plug in n equals 0, I have 0 plus 1 times 2 times 0 plus 1 times 2 times 0 plus 3 divided by 3. This is 1 times 3, so this is equal to 3 divided by 3, which is equal to 1. So the base case is true. Great. So again, these hopefully aren't difficult, it's just more doing arithmetic. So then when we move on to the induction step, so our induction step, we assume that this is true for n. So assume the statement is true for n. Now notice, in some of the proofs, I actually write out that statement. In this case, I'm not writing out the statement just because, I'll be honest, I'm lazy. That's a lot of stuff to write. So feel free to be lazy if you want. Just make sure you refer to it as the statement is what it is over here. Okay, so assume that this statement is true for n, we'll prove it is true for n plus 1. So again, if we think about what does that mean to be true for n plus 1, that means we're going to be plugging in n plus 1 into both of these. So I want to have a sum where the last term over here is going to be 2 times n plus 1 quantity squared. And over here, what it means to plug in n plus 1 is that this over here will become an n plus 2 times a 2 times n plus 1 times all of this. So you get the gist of what that looks like. So that's what it looks like. Now, we want to be a little careful because sometimes when it's true for n plus 1, how many extra terms will we be adding? In all of the cases so far, we've only really been adding one extra term. We could possibly have more that appear. So we just have to be careful. In this case, it's just nice and simple. We're just dealing with every consecutive odd number. So this is just going to be the next odd number that we're going to square. All right, so we can notice here. So notice we have 1 squared plus 3 squared plus 2n plus 1 squared plus 2n plus 3 squared. So this, if you plug in n plus 1, you get 2n plus 2 plus 1. That's 2n plus 3. So this is equal to n plus 1 times 2n plus 1 times 2n plus 3 divided by 3 plus 2n plus 3 quantity squared by the induction hypothesis. So by the induction hypothesis, indeed, we have these first n terms over here can be replaced by this. Now things are going to get a little dicey depending on how comfortable you are with manipulating these. So get creative, whatever you want to do. What I'm going to do is I see that there's a 2n plus 3 factor and a 2n plus 3 factor. I'm going to factor that out. So we see that n plus 1 times 2n plus 1 times 2n plus 3 over 3 plus 2n plus 3 quantity squared is equal to 2n plus 3, and now this whole thing becomes n plus 1 times 2n plus 1 divided by 3 plus 2n plus 3. And then what we have is something that's a little bit easier to work with. If I had to multiply this out and then try to factor things, you'll be factoring really nasty things. So now I can just find common denominators, and this seems a little bit better. So this is going to now be equal to 2n plus 3 times n plus 1 times 2n plus 1 divided by 3 plus 6n plus, actually I'm just going to take this as a 3 times 2n plus 3 divided by 3. Now, you can have a long string of arithmetic in your work as long as you're just staying on one side of the equation. So we're only working with this left-hand side still. I'm trying to just manipulate everything until it magically pops out to our end goal that we wanted to for n plus 1 being true on the other side. All right, so now if we look at this, I see that I'm going to have a 2n plus 3. And then now, well, all of this is over 3. Now, unfortunately, this is where we're going to have to multiply all of this stuff together. Unless you find a really sneaky way to do this, feel free to do that. But I'm just going to start multiplying. So I have a 2n squared plus n plus 2n plus 1 plus 6n plus 9. So I have 2n plus 3, and then this becomes 2n squared plus 9n plus 10 divided by 3. Okay, so when it comes to factoring this, you might be thinking, I don't really know how to factor that. If you do, awesome, factor it. But the helpful part is that we know what this should become. And so if we let the actual answer really push us in the right direction, that can help us know what this should be factoring as. Okay, because if we think back to what our original statement was that this was what it was true for n. So if we go back to this part, and if we look at this, if we simplify what that expression was for n plus 1, we would get n plus 2, and then we would get a 2n plus 3 times 2n plus 5 divided by 3. That's what we get if we plug in n plus 1 here. So notice over here, I have the 2n plus 3 already. I have the 3 on the bottom. Somehow on the top, I need these two things to appear. So if you think about multiplying these together, magically that becomes that. So I don't need to see your factoring steps. Just be like, yeah, great. This is 2n plus 3 times n plus 2 times 2n plus 5 divided by 3. Hey, there we go. Perfect. That's exactly what we wanted to, because that's what a factor does. So now if you want to make this really clear, if you're like, I'm not really even convinced of my own proof that this is true, you could rewrite this in terms of n plus 1s, right? This could be n plus 1 plus 1 times 2 times n plus 1 plus 1 plus, or times 2 times n plus 1 plus 3 divided by 3. So if you wanted to see that this statement really is the statement for n plus 1, you could rewrite it like this if you want. Then it really screams that it's absolutely clear that this is true. And then now we basically finished off the proof, and so we just have our final statements here. So then by induction, we see the statement is true for any n in the natural numbers union the set containing 0. So there we are. That is your proof for induction. So as you see from this example, don't be intimidated by long workings with algebra. Just try to work with factoring, expanding, and all of the regular steps that you're comfortable doing.